So the question is, which one is going to be in excess, and is there an advantage to it? There is. You want to have the carboxylic acid in excess, so you want that to be the ratio twice the amount of the alcohol. The reason for that is the carboxylic acid can be easily removed. What that means is you're going to have the reaction occur in the ratio of 1 to 1, which means you're going to have some unreacted, right? A good amount of unreacted carboxylic acid, which you need to remove. Between removing the excess alcohol and the excess carboxylic acid, it's easier to remove the carboxylic acid, right? The second way of, pushing that equilibrium forward is to remove water. Removal of water is done using an apparatus in the lab called the Dean-Stark apparatus. But you can also use a chemical called DCC, which is dicyclocarbodiamide. You don't have to know the expansion, but you want to know that it is a dehydrating agent. If you ever see it in any of the reactions, it's a dehydrating agent that is used to remove water. Okay. But this is the Fischer esterification process. It's a classic methodology. I won't say it's a great methodology, but it's a quick and easy one. We use it in the lab with a modification, and I'll talk about the modification as well later in this PowerPoint, but it's a straightforward method that leads to the formation of esters. So let's take a quick look at the mechanism of this reaction. So the first step, we're going to treat the alcohol as a nucleophile. So we got CH3 twice CH, so I'm just converting it into a condensed structure, CH2, CH2, and then OH. This is going to be our nucleophile. Our nucleophilic site, of course, is the oxygen. And then I'm going to take the carboxylic acid, which is going to be the electrophile. And the electrophilic site here, the site with the positive charge, is the carbon. So oxygen attacking the carbon, arrow 1, double bond O, becoming O minus. We've done this a few times. That's going to give us, so just go ahead and write the product we get out of this. So now it starts your equilibrium reactions. You can go both ways. You basically have proton transfer where the oxygen, which is positively charged, is going to lose the proton. So you're going to make that neutral, and the oxygen that's negatively charged is going to grab the proton. Then you're going to have another proton transfer where what happens is one of the hydroxyls is going to give the proton and the other hydroxyl is going to accept it. So one of them is going to act as an acid and the other one is going to act as a base. Which one acts as what doesn't matter. That's pretty symmetrical, and that's going to give you. So they're all equilibrium reactions, which is what causes a bit of a problem here. This becomes CO minus, and the other side becomes OH2. If you're wondering why that transfer happens, now you have a good leaving group. So now what happens is the O minus comes in, the water leaves. So that's going to give you your final product. I'll go ahead and write the product on the opposite side here. That's going to be CH3 twice CH, and then it's basically your ester. So this is the banana oil, which is responsible for the smell for bananas, and your side product is water. So I'm going to go ahead and just open this up a little bit. This part of it is acetate or ethanoate if you want to go. I strongly encourage you to go IEPAC, that is ethanoate. Now this is 1, 2, 3, and 4. Add 3, you have a methyl. So this is 3-methyl-butyl. So the name of this ester is 3-methyl-butyl ethanoate. Or you can say acetate, that's fine. This would be your IEPAC. So that is the mechanism of this reaction. If you want to give it a name basically what type of mechanism it is. It is called nucleophilic acyl substitution. The nucleophilic acyl substitution is the mechanism that has arrows 1, 2, 3, 4. Now, what is the setup for this reaction? So you would take the carboxylic acid, the alcohol, hopefully in the ratio of 2 to 1, okay? And then you would have to add concentrated sulfuric acid as a catalyst for this reaction. And you can see it involves strong heating. It's usually 1 to 1.5 hours of heating. You have a reflux condenser, which means you're going to reflux this at a constant temperature. So anything goes up, the water is going to push it back down. So you will not lose, any of the carboxylic acid or the alcohol. So you're going to reflux this. You're going to leave this open to air. Otherwise, you will have an explosion. You cannot heat a closed system. But you're going to drive the equilibrium forward by using an excess amount of carboxylic acid to ratio of water. And second, you're going to apply heat to push the equilibrium forward. So what happens is the heat will drive the water away as steam. What we are not doing is using DCC or using a special apparatus to remove the water. So at the end of this reaction, you're going to have your ester. Okay, I'm just keeping it general here. You're going to have your excess carboxylic acid. Assuming all your alcohol is reacted, you're also going to have water. This is going to be your product mixture. As much as you like to get only your product, that never happens in organic chemistry. It is mixed with some unreacted reactants and then some side products. Okay. So that is the setup. And then I'll talk about how you can separate this out. Now, in the lab, we do make a number of esters, and these are given in your lab flow as well. So we do them all simultaneously. So we will take multiple test tubes. We don't isolate our esters. We will add carboxylic acid, alcohol, sulfuric acid. We put them all in water bath in a specific arrangement. And then we have coffee beans, and then you will just move from one test tube to the other, waft the vapors, and we actually make a series of 15 to 20 esters of different smells. And these are your artificial, fragrances for the different esters. And I think one of them you're asked to make, I think raspberries or something, and we'll look at it. But these are the esters responsible for these fragrances. So it's kind of a good list to have. That's about it with your reaction. I want to start looking at some pre-lab and post-lab questions to explain a little bit more chemistry. So draw the structures of the carboxylic acid and alcohol needed to make an ester that smells like pineapples. So we are going to look at this particular ester, which is your ethyl butyrate. So what I'm going to do is go ahead and just open this up a little bit just to show you how we can decide, what our carboxylic acid and our alcohol are. So what you want to do is a couple choices you have. I like to just cut it right there. But if you cut it right here, you still get the right answer. But I like to cut it there because I know that this section is going to come from the alcohol. Mechanistically, this comes from the alcohol. This comes from the carboxylic acid. You got to figure that portion of it out. So then we can set up the equation. This will be your carboxylic acid. That's a total of 4 carbons. So this is your butanoic acid. And then we have ethanol. That's just 2 carbons. And we should not forget that it is going to take place only in the presence of sulfuric acid. That should give us our final ester. Okay, so you can just redraw that structure there. So that is how you want to decide. You want to kind of just go right through this area. I like to cut it there, but if you went to the right side of oxygen and sliced it, you still get the right answer. But mechanistically, this is how it is. Now, one other pre-lab, I'm not answering all the pre-lab questions, just a few. I think the second one is quite straightforward. I think you'll be able to answer. This third one, why esters are more volatile than carboxylic acid and alcohols. So what I like to do is just keep it general here, we'll go ahead and write the ester, and then we're going to write the carboxylic acid, and then, of course, the alcohol. So when you get to something like this, something where you have to comment on volatility, boiling point, or something like that, esters are more volatile, which means higher volatility, so lower boiling point, which means these guys are less volatile, so they have higher boiling point. So we want to look at the different intermolecular forces. We have van der Waals forces all along. Then you have your dipole interactions in every case. But then there is no hydrogen bonding in the esters. You have 2 hydrogen bonds per molecule, and you have hydrogen bonds here. So I would expect this to be the most volatile, this to be the least volatile, of course, and the other one right in the middle. So least boiling point for esters, and now you can see why they make good, fragrances, essential oils, and so on. But not so volatile like a hydrocarbon that you can't put it in a bottle. Yes, you can put it in a bottle, but as soon as something touches your skin or your nasal membranes, the body temperature is enough to volatilize it. But your explanation, when you talk about boiling points, melting points, water solubility, or any kind of solubility, volatility, surface tension, all of that has to come from intermolecular forces. So, one other pre-lab question I want to talk about is acid chlorides are very good sources of the acid for the formation of the esters. So you're asked to compare the reaction of a carboxylic acid with an alcohol, and then compare the reaction of an acid chloride with an alcohol. So we are going to start with a carboxylic acid, which is what you're studying in this particular. So you need sulfuric acid in this particular lab experiment, and that's going to form this, okay? You're asked to compare this with an entirely, different starting compound, which is the acid chloride, alcohol, forming the ester. Here, of course, your side product is water. Here, of course, your side product is HCl. When you have HCl, remember, typically we use pyridine. Pyridine will remove the hydrochloric acid. It acts as a base to do it. We have done that a few times. Now, the top one is called the Fischer esterification. I just mentioned that, and then you probably know that very well. The bottom one is called a modified Fischer. The modification here is that you're not using a carboxylic acid. Instead, you're using an acid chloride. When you have a modification on an existing procedure, that's really to take care of the problems associated with the existing procedure. The problems associated with the existing procedure is, big problem is, it is an equilibrium reaction. That is really the biggest problem. But this one right here is not an equilibrium reaction. So your comparison there, products formed in both cases, the major product is an ester, okay? This one is less reactive. A carboxylic acid is less reactive compared to an acid chloride. This one is more reactive. We already know this is a more reactive. So therefore, it's a faster reaction. Slower reaction requires high temperatures and takes a long time. Because it's an equilibrium reaction, you have to use a ratio of 2:1 of carboxylic acid and alcohol. I still haven't explained to you why it needs to be twice the amount of carboxylic acid and not twice the amount of alcohol. But there is a question that addresses that, and I'll get to it at that point. But nevertheless, the reaction is going to be a 1:1 ratio, which means it's going to leave you with an excess of the carboxylic acid that you have to deal with. This reaction is a 1:1 reaction. You don't need excess because it's not an equilibrium reaction, it's a 1:1 reaction. Although hydrogen chloride or hydrochloric acid is a side product, you're using pyridine. Pyridine will combine with HCl to form a soluble salt. What I mean by soluble salt is it will dissolve in water. So if you add water and shake it, you get rid of one of the side products and leaves you with a very pure ester. So overwhelmingly, I would say this is a much better method. Okay. So in comparison, you're comparing that one is equilibrium, the other is not. One storing compound is less reactive, the other is more reactive, and so it's a slower reaction, requires a higher temperature. The fact you're using 2 to 1 is a problem as a chemist for you, because the reaction is a 1 to 1 reaction. You're doing it as 2 to 1 to push the equilibrium forward, which means you have to deal with getting rid of that excess chemical. Here, you don't have to do that. It's a 1 to 1 reaction. So that is a question, I believe, in pre-lab that I wanted to address. Next is calculation of the theoretical yield. As I've said, it's a 1 to 1 reaction. We should make it. At this point, you guys are doing really well with the calculations. So I know it sometimes you get an oddball answer, like more than 100%, depending on what you choose. As long as you're confident of the calculation or you want to check with me, that's fine. But let's just look at the theoretical yield calculation. What you will do is start with mass of, you have to do 2 calculations here, one with the alcohol and one with the carboxylic acid. So we're going to start with mass of isopentyl alcohol. You may take the ratio of 2 to 1, but the reaction is 1 to 1. So remember that. It's going to be 1 mole of alcohol divided by molar mass of alcohol times, it's a 1 to 1 ratio. That's what I wanted to stress on. So I know I kept saying 2 to 1, but that's to drive the equilibrium forward. So careful here. So this is 1 mole alcohol and then 1 mole ester. Then you want to go 1 mole ester. And top is going to be molar mass of the ester. So you need to calculate the theoretical yield using mass of isopentyl alcohol. Remember to calculate the theoretical yield using the carboxylic acid, which is acetic acid. Okay, you have to repeat it, and the ratio is again 1 to 1. So it's 1 mole acid times 1, to 1 mole of the ester. So similarly, the one that's going to give you the least amount of yield is your limiting reactant. So there are a couple calculations I need to see. In fact, LabFlow will ask you to do both. You lose points if you don't, so put it in. And it should be a much better experience for you compared to the Grignard. I know a couple of you, it acted weirdly on the Grignard, but this is going to be straightforward. I did a little calculation myself. I didn't have any issues. It seems straightforward, but if you have any issues, please do address that, send me an email. I've done some grade adjustments with some of you for the Grignard. So limiting reagent is based on your calculation, okay? Now, you're asked to identify the boiling points of the esters and the alcohol. This is your ester, and this is, of course, the alcohol. The ester is 142 degrees Celsius. The alcohol is 131 degrees Celsius. The reason you're asked that is because in the separation, there's a fractional distillation, and that is going to lead us to the next question. That's why we want, the boiling points, and I will connect. I mean, I just don't want this like sticking there, like making no sense. I'll connect the next question to this, and it'll have better significance. So now what we're going to do is show a separation scheme. So we'll draw a flow chart which shows the isolation of isopentyl acetate. So keep in mind, we are starting with the carboxylic acid. We don't have to write the exact structures. We are using the alcohol, and we are getting this isopentyl acetate, which is an ester, and water. So the end of the reaction, no matter how much you push the equilibrium forward, you're really successful. It's still an equilibrium reaction. You're going to have the following. You're going to have the ester. It is going to be contaminated with some water because we are not employing any method to remove water. You're going to find out what the limiting reactant is. Invariably, you're going to have carboxylic acid. Either it's going to be excess or it's going to be some unreacted carboxylic acid because it is still an equilibrium reaction. So you're going to have a little bit of that left. You're going to have alcohol. Hopefully that's not in too much excess. But whatever it is, it could still be some unreacted. Because of this little backward arrow, you're just going to have all these four. And don't forget that you're going to have concentrated sulfuric acid, which will be regenerated. That's your catalyst. And that's why you're asked to come up with a separation scheme of how do you get what you want from this mixture. So let's go ahead and look at the separation scheme. So we are going to start with, I'll keep it very general and say reaction mixture, and that's totally okay. So when I say reaction mixture, it contains 1 through 5. It contains all these guys here. First thing, you're going to add water. All of this is given in the procedure. I'm just converting it into a flow chart, okay? So when you add water, it's going to divide into 2 layers. You're going to have an aqueous phase, or you can call it the aqueous layer. And then you're going to have an organic layer. Now, in the aqueous phase, take a look what all can mix. Your alcohol is not going to dissolve in water. If you're wondering why, you want to go back to the structure of the alcohol here. This is a little bit of ethanol. All of it is not going to dissolve. Some of it will. Your carboxylic acid has 4 carbons. It's, some of it can dissolve, but not all of it. But what can really dissolve is your water can mix, your concentrated sulfuric acid can go away into that. Some of your alcohol, very small amount, even smaller amount of your carboxylic acid. Your ester is not going to go into the aqueous phase. Again, keep in mind, not all the alcohol and the carboxylic acid will go. How do we indicate that? Some of it. Okay, some of the alcohol and then some of carboxylic acid. I don't want you to think that we have successfully removed all of them. Now, this phase is going to contain your ester. All right, it's going to contain your carboxylic acid. A lot of it is going to be there, and maybe even your alcohol. But it's definitely not going to have water and concentrated sulfuric acid. Okay, this one is discard. We don't need this. Now we move to the organic phase. Now what I do here is add sodium hydroxide. I'm not even specifying the concentrations or anything, It's a very qualitative flow diagram if you want. So this is going to give us an aqueous phase and an organic phase. Now sodium hydroxide is basic. So what's going to happen is the carboxylic acid will react with sodium hydroxide to form the salt and water. We don't want the carboxylic acid, so discard. Sodium hydroxide is not a strong enough acid to react with an alcohol because, sodium hydroxide is not a strong enough base to react with alcohol. Alcohol is a weaker acid. Carboxylic acid is a stronger acid. So it's only carboxylic acid that's going to react. We don't need to do anything with this aqueous phase. We discard this. Now, this is going to contain ester and maybe some unreacted alcohol, but this is going to be your major amount. This is going to be a minor amount. Remember, we have worked very hard in pushing that equilibrium forward, but still you got a little bit of the backward reaction, right? So you're going to have a little bit of that. Now, to this, you're going to add sodium chloride solution. Sometimes you can also add calcium chloride, but that's not going to be an aqueous solution, that's a solid. Okay, it's not going to divide into sort of 2 phases if you add calcium chloride, so careful. If you add sodium chloride aqueous, it's going to divide 2 phases. You're going to get an aqueous phase and you're going to get an organic phase. So the alcohol is removed in this, some of it. Okay, some of it is removed here. Not all of it again, some of it is still removed, but it's going to leave very little behind. You're going to have ester plus alcohol still, a really minor amount is there. The sodium chloride with water can remove alcohol out. Calcium chloride can complex with it. So in our lab, we typically use calcium chloride. So we add calcium chloride. So what happens is calcium is divalent. So it just complexes like this. And then we have H plus, Cl minus. So it's a nice way to get rid of as much alcohol as possible. Sodium chloride can do the same thing. So all it does is complexes. It's just like a Lewis acid based complex. I wouldn't read too much into it, but you get the idea. Okay. Now, to this, it's common so much contact with water. This organic phase is going to be contaminated with water. So you're going to add anhydrous sodium sulfate. This is a dehydrating agent. Now, it's not going to remove large amounts of water. So keep that in mind. It removes trace amounts of water. So no really chemical reaction. You get a dry. At the end of all of this, I'll make this arrow a little bit bigger. At the end of all of this, you're going to get dry organic layer. This is still going to contain your ester, which is your major amount. You have worked very hard in removing as much alcohol as possible, but it's going to be contaminated with a little bit of alcohol. This is going to be distilled. And this is why we needed this temperature. In the distillation, your first fraction is going to be the alcohol boiling off at 131 degrees Celsius. Your second fraction is going to be your desired compound, which is ester, 142 degrees Celsius. So that, in a sense, let me just blow this up. You're probably still writing this. That, in a sense, will be your separation scheme. So it's an exceedingly lengthy lab. When we try to make an ester and we isolate it, it's quite tedious because you are waiting for 1.5 hours, with the Fischer esterification with the reaction, and then you have to work really hard. So when we have a better method like the modified Fischer, that's what we do. At Williams campus, we just do that. It just makes more sense because we only have 3 hours and we try to finish as much as we can. Okay, so take a quick look at this flow chart and let me know if you have any questions, anything needs to be blown up. Everybody good? Yeah, that was the last part. Make sure you got it all. Okay, that is your first post-lab question. And then we want to look, there's only one more. Almost done here. So we have to look at the literature and the experimental IR spectrum for the isopentyl acetate. So this one is from LabFlow. I just want to make sure you have to assume that this is the experimental one. This I got from LabFlow, okay? Now this is the literature one, excuse me. This one I got from this open source resource. It's a nice website. You should check it out, SDPS. So we want to compare. So we are really looking for this ester, functional group where I'm really looking for the carbonyl, which is right here. So this is the carbonyl stretch. I was just estimating. That is 1750 wave numbers. And this one is the carbon oxygen stretch. That's a single bond stretch. So this is 1, this is 2. So this is your 1 and this is your 2. So this is like 1220, something like that, wave numbers. Maybe even less than that. So that is your experimental. That's what you would have got in the lab. And right here is your carbonyl stretch. So that's your 1. So that's approximately 1750 wave numbers. And right here is your carbon-oxygen stretch. That's your bond number 2 that I've labeled as 2. Yeah, it's also approximately 12-ton wave numbers. Now, apart from that, we're also looking at these. Okay, so let's take a look at this one. This is going to be your carbon-hydrogen stretch. That's approximately 3000 wave numbers. Carbon-hydrogen stretch, 3000 wave numbers. Now, let's go ahead and expand on this a little bit to talk about one other thing. So we got R, right? And then we got a C double bond O, and then we got some more carbons here. So I call this 1. I call this bond 2. Remember, there's another oxygen carbon bond there. And that's 1 is right here. That's your 3. That's also your carbon-oxygen stretch. Esters have 3. So 1100, 1200 is approximately 1300 wave numbers. And that one is right here. 3. To get rid of the arrow first, the cheek. So that one's coming around 1350 wave numbers. That's your 3. So you actually have 2 carbon oxygens stretches, unlike your carboxylic acid or something like that, where you only have 1, you have 1 and 2. You don't have the 3, right? So you want to see the difference there. So 1, 2, 3 are your characteristic stretches. So why I wanted to point out is identifying the bond in the structure corresponding to at least 3 peaks on each spectrum. I would say 1, 2, 3 are your key peaks. Your carbon hydrogen, I don't really give it much value. You can mark it, but I don't think, that's what we're talking about. When we're looking at the functional group, I think we're talking about, 1, 2, and 3. Those are the 3 stretches we're talking about. So this should pretty much answer all the questions in lab flow. Now, I can remember I have to go in and check. Now, this is essential for both of us because grades are due Friday during finals week. And I have a feeling I made this, I didn't give you a week. I made this due this week. So I would like you to tell me if you like it postponed to next Monday. I'm okay with it, except that Monday is a week of finals. I didn't really want to do that. Unfortunately, I had to have a lab today. If it was face-to-face, we don't have a lab 1 week before the finals. Because it's internet, we have to have that lab today. So the point I'm trying to make is, let me take a quick look. I have a feeling this is due. Yeah, this is due May 10th, and I can postpone that. And this is due May 14th. So my question to you is, do you want a postponement on that? That is Friday. I could make both of these due May 16th. Will that help or not? You have to let me know. If it helps even a few people, I'll just change it, and that's okay. But what I don't want you to do is try to turn it in after it's locked, because then Canvas does some goofy stuff, right? So let me know. I'm just waiting for you to tell me that, and then that's about all we have for today. If you think you can get this all done by Friday night and just have a free exam week where you just focus on all your courses, that is also good. But I will change the pre-lab to 14th, and I'll make sure of that. And then if you've already turned it in, I will increase the number of attempts so you can turn it in again. But do you want the 14th to become 16th? That's what I would like to know. I think taking it to next week is not a good idea. You guys are really quiet. So you're okay with 14? Go ahead and turn it in. That's fine. Anyone else who needs it for 16th, let me know. I've given you all the information, so I'm thinking you should be okay. And we are done with this. The extra credit, I would really strongly recommend that you don't attempt it if you don't need it. 90% and higher is an A. Whether you make 98 or 90 in Maricopa, it's an A. We don't have plus and minus. So don't waste your time attempting aspirin. I know it's an interesting lab, but you got exams next week. So just play it smart, okay? Okay, that's all I have for today. If anyone else feels they need an extension, let me know, but I will change the pre-lab to 14th. Okay, I'll definitely do that. But other than that, I don't have anything else. If you have any questions, let me know. If not, we will